Hi, everyone. Thanks for coming. I know it's getting late in the day, and after all the hallway conversations and the other talks you've been to, you start running out of steam, so I appreciate it. My name is Ryan Barrett. I'm one of the co-founders of Google App Engine, and I'm the lead on the datastore right now. And I'm here to talk about multihoming, so running a service from multiple data centers. This is the kind of thing we do over the weekend when we get bored and we don't have any parties to go to. So figured we hacked this together last weekend, and I'd give you a quick demo. So we're going to be taking questions using Google Moderator. And so if you go to this URL, codegoogle.com, eventual questions, go to the App Engine track and the transactions across data centers series, and feel free to type in questions, vote on questions, all that good stuff. So let's get started. I'm going to start with a couple quotes. One is from a guy named Eric Brewer, who is a professor, a computer science professor. He's also done architecture at Berkeley. He's also a co-founder of Inktomi, which you might have heard of. He's well known for this theorem, the consistency, availability, partition tolerance theorem. And so the idea is if you have a distributed storage system, this is just an inherent trade-off that you can't get away from. And so you better acknowledge it early and pay attention. It's not black and white. You don't just get 2 out of 3. Often you can give a little on one and get a little better in another, but this is something we pay attention to. He's also a wicked smart guy. The other one is not as interesting, but there's no free lunch. Making something scalable is just plain hard. You can use a bunch of different technologies. You can use a bunch of different techniques, and they get you a long way, but you can't just stick your head in the sand and ignore it altogether. You got to pay a little attention, and so this is what we've done. So before I get started, one of the best pieces of advice I ever heard about presenting is that whenever you switch slides, what everyone does is stops listening, reads through the slide, then turns back to you and starts listening again. So what I want you all to do is whenever I switch slides, turn away from me, look at a screen, then when you're done, turn back to me, and I'll actually know that I can start talking. Because I know this is what I do. If I'm not on my laptop at a talk, this is what I do. So anyway, multihoming, like I talked about, serving something from multiple data centers. Hard problem, but we need to figure out how to do it. There are a lot of parts of this, and I'm not going to get into most of them. Actually running a serving stack, most of the stack, for example, offline data processing, batch processing, MapReduce, long-running, data mining and analysis, that kind of thing. Read-only data, content distribution networks, CDNs like Akamai. All these things are really interesting problems in their own right, and I only have an hour, and I even have more than I can fit in an hour. So I'm going to stick with what I've been working on the last few years, for a while now. It's what we call structured data, user data that is both written and read. Often by your users, and when they take actions that write data, they often expect to see the results of those writes, and expect some guarantees on consistency and availability and that kind of thing. So in my humble opinion, or the biased view, this is one of the hardest kinds of data to run a data storage system across data centers. So we're going to talk about a few ways of doing this, how App Engine currently does it in some places, and kind of throughout, I'm going to talk about the App Engine data store and what the choices were we made, things we went with, things we didn't go with to run across multiple data centers. And again, as a disclaimer, there are a lot of great talks at this conference on best practices for how to write an App Engine app, new features, that kind of thing, and this is not one of those. I will be talking a little bit about App Engine, but mostly just how we did things. Mostly it's just going to be general lessons learned, both good and bad. So I'd encourage you to go to some of those other talks too. This is more just kind of stories. So specifically, what are we going to talk about? First thing is consistency. What kinds of guarantees do you have from a cloud data system? How are they similar and different from databases and other data storage systems you might be familiar with? Transactions specifically, what are they apart from consistency? Why do you need them? How do they interact with multihoming? Why do we need to do multihoming at all? I mean, can't we just serve out of one data center? Then we're going to actually get into the details, talk about specific kinds of multi-homing, specific techniques that you can use, and finally some conclusions. So there are 3 kinds of consistency I'm going to talk about. There are more. If you were in Dan Wilkerson's talk on distributed transactions, you heard about causal consistency and a few others. But here we're mainly going to focus on what we call weak, eventual, and strong consistency. And as a concrete example for each of these, we're going to look at what happens when you do a read, when you read an object after you wrote it. So the first one we're going to look at is weak consistency, and this is the most text I've had in the slides so far, so please look at the slides and read, and when you're done, let me know. Weak consistency is what you get from caches. That's the best way to think of it. You don't really have any guarantees. You put something in, later you ask for it, it might be there, it might not. You might never get it after you ask for it. You know, the cache just might be churning so much that things are constantly evicted. This is what we call best effort. I think of it as message in the bottle. The Memcache API in App Engine, it's just a simple kind of unified large-scale in-memory cache system, is a perfect example of this. VoIP and kind of online streaming media are great examples because often if you lose connectivity and you miss some messages or they come in delayed, often you don't care. If you're talking on the phone, and there was a hiccup, you don't want it to try to catch up and get behind. You still just want that real-time communication, and so you're okay with it dropping some packets. And so some writes or some messages that came from the other side never get to you. But that's okay, because that's the use case, that's what you expect. Low-latency multiplayer games, so first-person shooters, that kind of thing, stuff that you play online often are the same. Sometimes you interpolate. Sometimes if you just have old state, you don't really care about where the other guy was, 30 seconds ago. You care about where they are now. So there are many cases where weak consistency is good. It's the right trade-off. But for data storage systems, stuff that's persistent, it's weak. Eventual consistency is better. There are great examples of this. The idea is you'll eventually see the stuff you wrote. You just might not see it right away. The email sending API in App Engine, and email in general, SMTP for mail delivery is a great example of this, where you send an email, you accept that it's not guaranteed to immediately show up in the other person's inbox as soon as it returns from that send operation. But you know it will get there eventually. The Postal Service, despite their budget woes right now, same kind of thing. DNS, domain name propagation, changes to that is similar. There's some notable cloud platforms, Amazon's S3 and SimpleDB, also a SimpleQ service, are eventually consistent systems. So if you write a file into S3 or you write a record into SimpleDB, you won't immediately see it, but you will see it soon after. So in SimpleDB, I think in practice, you see the results of writes in a few hundred milliseconds. I think they average around 400 or 500 milliseconds, sometimes up to a few seconds. S3, I'm not sure about. But this is much more useful. It's not ideal, though. The ideal kind of consistency for a read-write or structured data system is strong consistency. You get what you put in. This is the simplest one to think about and to program against, in my humble, biased opinion. So you're guaranteed when, after you do a write and it returns successfully, it doesn't throw an exception, any read after that will see it. The App Engine data store works this way. File systems almost always work this way. Relational databases. Microsoft Azure. Not enough people talk about Microsoft Azure. I think it's actually fascinating. They've made a number of really, really interesting and compelling design decisions. Their competitor to SimpleDB and the App Engine data store is called Tables. They're also strongly consistent. So these are 3 forms of consistency, weak, eventual, and strong, that depending on how we build a storage system, we're going to see one or more of these. And we want to pay attention once we try to move a system like this across data centers. Do we get the same guarantees? Have we lost some guarantee? Sometimes it's okay to lose some of those guarantees, but you want to know. So that's consistency. Next is transactions, and for those of you who are in Dan Wilkerson's talk, feel free to go to sleep for 5 minutes, and I'll wake you up when we're done. Transactions are kind of an extended form of consistency across multiple operations. The cliched example is a bank. You need to transfer money from A to B, or as in Dan's talk, from Alice to Bob. There are two separate operations here, subtracting money from A, adding money to B. Since we work with computers and within a single thread on a single machine, operations are serialized, you can't do those at the same time, and something bad could happen in between. Something else could come in and read from A or B, or write to A or B. The thread in the machine that you're running this transaction in could die for any number of reasons. On App Engine, maybe you hit the deadline, the request deadline. There are a number of other possibilities. You don't want to be in that position. You want some guarantees that if you die in the middle, the invariant will be maintained. Either that money subtracted from A will go back to A, or the money added to B will eventually still get added to B, because, as Dan said, this case where you've created money or destroyed money, you're not really allowed to do that. Only the Federal Reserve is actually allowed to do that kind of thing. And we're not trying to get in the business of banking. We just write software, and we like it there, and we want to stay that way. So we like our transactions to be transactional. So this is just a more abstract way of saying all that. Transactions give you broader consistency, correctness, enforcing invariance, and there are 4 traditional properties that people describe. Transactions are atomic, consistent, isolated, and durable. And any database textbook will go into details here, but these are nice properties of transactions. And just like consistency, they're hard enough when you're operating on one machine or on a few machines inside a data center. When you start operating across data centers, again, you want to pay attention to what could happen to transactional guarantees that you had before you started spreading out all of your work. So, we've talked about consistency, we've talked about transactions. Now let's get into the more interesting background. Running one data center is hard enough, usually. Why would you want to run more than one? So there are some good reasons. Catastrophic failures are the thing no one really wants to think about, but what if your data center fell into the ocean? More realistically, what if there was a fire, which does happen? What if the power went out for a couple hours, which is not quite as violent? You probably won't lose any data, for example, but you're down. It's no fun. There are also a number of expected failures. So there's hardware that kind of operates at the entire data center level. In the NOC, the Network Operations Center, for example, there are lots of big iron routers. There's the power, as we talked about. There's cooling. There's backbone connectivity in and out. Any of these things, they're usually they have good uptime, but nothing lasts forever. And so the more hardware you're operating within a data center, the more likely it is that at any one time, something's going to fail. So you don't like it, but you expect it. One of the things you do to prevent that is routine maintenance. But the problem with maintenance, again, is it takes some piece of software off, or some piece of hardware offline. Finally, we call it geolocality. It's a big word for putting stuff near your users so their requests get to it and back fast. We like this. In the US, we are somewhat spoiled, and it's easy to ignore the benefits of geolocality because lots of stuff is here. And we have good backbone connectivity to everywhere else. If you ever spent time in China or India, there is kind of a mixed bag in terms of network infrastructure at best. If you ever spent time in Australia, good network infrastructure, but it's just far away. You really start hitting speed of light constraints. How long does it take, even without routing delays or queuing delays? Just that speed of light to get a packet from Australia to the US and back is a while. I don't know that number off the top of my head, but I know a round trip from the west coast of the US to the east coast of the US is 30 milliseconds. And that's purely speed of light, no routing and queuing. And if you go through some of the big peering points, Pax East, Pax West, May West, God help you. They're always overloaded. And they're going to add another 30, 50 milliseconds without breaking a sweat. So when you can operate multiple data centers, some close to your users. It helps you. CDNs like Akamai are masters of this, and Amazon's FileFront and a number of others. What you often do is what we call edge caching. Data that doesn't change often, you throw it all over the place. You try to get it as many places and as close to as many people as you can. So these are some of the reasons you do want multi-homing. But there are plenty of reasons you don't want it. Within a data center, everything's nice. It's every now and then we talk about it's like being in the womb. It's warm and comfortable, and you don't have to go anywhere, and everything's there for you. Between machines inside a data center, you have really high bandwidth. You have really low latency. And usually that networking cost, no one charges you for bandwidth within a data center. It's generally free. This is a nice place to be. All this stuff is more or less the opposite across data centers. Much smaller pipes, depending on which company you're going with for backbone connectivity. Often they're very small. And you can find bigger ones, but they cost money, a lot of money. Higher latency, like I was talking about, a round trip between two separate points, especially if you're going across one of those big oceans. I mean, the Atlantic and Pacific are big places. That speed of light getting across them and back takes a while. And finally, like I mentioned, that network connectivity costs, and it's not cheap. So if you can help it, you don't want a multi-home, not unless you absolutely have to. So, sorry, I should do the wrap-up. Consistency, transactions, and now why multi-home. So, yeah, this is more the same. Like I said, this is a hard problem, particularly hard if you are running, like I talked about, a read-write data system with user data where as soon as you start accepting writes, for example, in more than one location, you're going to have inconsistency. If I try to transfer money from Alice to Bob over here, and I try to transfer money from Alice to Eve over here, and Alice doesn't have enough money for both, if you let them do that, and then they try to reconcile later, again, you've created money or you've given Alice credit where you probably didn't mean to. And so maintaining consistency in the face of that distance and managing those connections is not trivial. So what do we do? Like I said, often you just want to avoid this entirely. And lots of people do. And there's a lot to be said for this. Solving hard problems is by definition hard. And the more hard problems you try to solve, the less likely you are to be good at any one of them. So lots of people just don't. And more power to them. Often, the way you do this is, we use the word bunkerizing. You bring in 5 sources of redundant power, and you have 4 separate companies that give you backbone connectivity, and you have cooling that ranges from massive water-cooled systems to ice that you picked up at the 7-Eleven, but you pick up that ice every day, and you pick it up from maybe 2 different 7-Elevens just so that's redundant. So, regardless of what you're using to cool, you got something, and you got 3 others in the back. Bags of ice in the trunk, just in case your big water-cooled system goes down. Lots of people do this. Microsoft Azure right now serves out of, I've forgotten exactly what they said. I believe they only say North America, not U.S., but they right now offer 1 U.S. location. In the future, they will give you one North America location. In the future, they will give you the choice of 2 North America locations, but no help in running something across them. Amazon SimpleDB, from what we know, is similar. I believe there are real-time backups, but unlike most of the other Amazon Web Services, you can't choose a physical region or availability zones for SimpleDB, and I'll get more into this in a bit. All the reasons we talked about for multi-homing are reasons why you don't want to, or why not multi-homing are bad. One is if it is a destructive or somewhat destructive problem that happens. Fire, the falling into the ocean is the example we all use. Not going to happen, but it's very colorful, so it's always fun. You could lose data. We always talk about backing up and replicating across disks because we know disks and machines fail. But sometimes physical locations fail too. Fire, hurricane, whatever. And ideally, you don't want to lose data because of it. Data loss is pretty much always bad. I don't know how many of you noticed the recent SVColo outage. SVColo is a data center that is located in Silicon Valley. Recently had a power outage for 2.5 hours. People noticed only because Twitter and FriendFeed were singly homed in SVColo, and so they're both pretty popular. Hands up if you use Twitter. And okay, so just out of curiosity, hands up if you use FriendFeed. All right, okay, good stuff. The FriendFeed, one of their co-founders was the original product manager on App Engine, Brett Taylor. Good guy. But poor companies, they were singly homed. They were down for 2 hours straight, 2.5 hours or so. They came back up. They didn't have any data loss, thank God. But they were still down, in the middle of the day for 2 hours. No one wants that, and not their fault. SVColo should have had some more redundant power, but it happens. Often what happens is human error, where no matter how much redundant power or connectivity you have, someone presses the wrong button. That's the cause of many outages. So these kinds of things, if you don't multi-home, this is what you might be in for. Finally, that geolocation thing we talked about, being close to users, now more than ever, your users are everywhere, physically. They're connected, but connectivity is not flat. There's a great quote from, who was it? I forgot. I think it's one of Tim O'Reilly's favorite quotes. The future is here. It's just unevenly distributed. Connectivity is the same way, very unevenly distributed. So yeah, if you're in one data center, everyone's got to get there. And so the people who are far away, it's going to be slow. The next option is you run multiple data centers, but it's similar to MySQL master-slave replication. Only one of them is your master. The rest you can serve reads from for this kind of read-write database-style data, but you don't serve writes from them. You serve writes from the one master data center. This is better, obviously. It handles catastrophic failure better. You still have your data in other places. Since you're replicating asynchronously in the background, there will be some window of data that was kind of on the wire or hadn't quite made it out of the data center. If a data center falls in the ocean, that small window that hasn't made it over to another data center is probably lost. In reality, it doesn't fall into the ocean. It just goes offline for a while. Comes back up, you get that window of data back, usually. But it's not available while the data center is down. And if there's something destructive, often you've lost it entirely. Finally, depending on what kind of technique you use, and we'll get into details in a bit, the data in your other data centers may or may not be consistent. It may not be consistent at all. It may not be consistent with regard to your transactions. And so this is something to pay attention to as we get into techniques. Examples of this, Amazon has done a good job of making physical location and availability zones, like different data centers, more transparent. So if you use EC2 or S3 Simple Queue Service, you can choose where your VMs in EC2 or your files in S3 are located in the US or the EU. So you can choose your master, at least. EC2 also gives you a choice of what they call availability zones, which are more or less separate or physically separated data centers within that region. I actually had to change this slide recently. They announced scaling, load balancing, monitoring, stuff that will help you effectively multi-home across their availability zones, which is very exciting. We've been inspired by a lot of stuff they've done, and so we continue to get excited about features like this. Many financial institutions use this kind of multi-homing. You hear about credit card companies with data vaults, under 6 feet of lead underneath, I believe it's Iron Mountain in Virginia or a few other locations. Makes you think of the old days in the 50s with bomb shelters. It's kind of a little scary story, but it's always it's fun to go actually tour one of those sites. Finally, you get some geolocation here. All of your slaves can serve reads, depending, again, on, we'll look at the techniques, depending on what kind of consistency and respecting transactions that you expect. If you're careful, your slaves can serve reads, just like, again, MySQL replication, which a lot of you who have used LAMP stacks might have used. But you still only have the capacity of one data center and the geolocation of one data center for writes. The last option is the holy grail, true multihoming. You have lots of different data centers. They're all serving reads and writes. They're all magically consistent. They, transactions just work. That's really hard, really hard. It's hard, so there are a number of examples that do it with just 2 data centers. One of my favorite stories here is, I believe this might be an urban myth, but NASDAQ. There's a story about how NASDAQ runs 2 data centers near each other for that whole speed of light thing, and they do 2-phase commit across the 2 data centers. So every single trade or every single transaction on NASDAQ is guaranteed to atomically be persisted to either both or neither. So the story is they had to go buy some networking equipment at some point. And they walk in and they've got their purchasing manager and a bunch of engineers come to do testing. And they're carrying these suitcases. They got like 5 suitcases. They look heavy, and then the networking equipment vendor looks at them and says, "Hey, what's that for?" And they open up the suitcases. They're full of fiber. And they say, our data centers are 27 miles apart. This is exactly 27 miles of fiber. Our algorithm, our 2-phase commit thing, works if you give us like a 2 or 3 millisecond window. So if you can guarantee, we're going to hook it up, we got this 27 miles of fiber. If you put one of your routers over here, one of them over here, we'll do some measurements. If you hit like that 2 millisecond window, we can do business. Otherwise, we got to take our fiber over to the next guy. So they do it across 2 data centers, and that's hard. Doing it across multiple data centers, more than 2, is fundamentally harder. On the plus side, you get all of the benefits. This does the magic for you. You handle catastrophic failure, expected failure. You can serve people from whatever data center is closest to them. Naturally, if you can do this at all, you're going to pay for it. Queuing delays, routing delays, speed of light, all of that. You got to talk between data centers, and it's just fundamentally slower and a smaller pipe. So sometimes you might also pay for it in capacity or throughput, but you'll definitely pay for it in latency. All right, so we've got through the bulk of the background. Again, we've talked about consistency in transactions. Why do you want a multi-home, and what are some of the kind of broad categories of multi-homing that you might see? Let's get into some details, like how do you actually do this if you're building one of these systems? So this is kind of the broad outline for where we're going to go in the next 15 minutes. Down the left side are things we care about. This is how we want to evaluate different techniques that we're going to look at. What kind of consistency in transaction support do we get? What kind of latency, throughput? If something happens, will we lose any data? How much data will we lose? And when we have to fail over, if there is expected maintenance, or if we need to move things, say we're decommissioning some data center, we need to turn up another one. What we call failover, basically moving some serving capacity from one data center to another. How do we do that? How well do the techniques support it? And this is a kind of preview. The actual techniques that we're going to discuss are across the top, and I'll get into detail right now. Backups, we all know and love. We all say you should back up, and to varying degrees, we actually do back up. Our laptops, our phones, that kind of thing. Your data as a company or an organization is no different. You got to back up at minimum. So this is Sledgehammer. You make a copy of all your data. You got it, and you got to keep it somewhere, and make sure it's stored and archived for a while so that it lasts. But the nice thing is you got this entire copy. I said weak consistency here. It depends. So depending on how you've designed your system, if you can back up at a consistent snapshot, whether you use timestamps or versioning or whatever, then you can maintain some consistency, and often you can maintain transactions too. The majority of time, backups don't work like this. Mostly you start reading and copying at the beginning of your data, and you go through to the end. It might take a few hours, it might take a day, it might take a week. And so you see an earlier state at the beginning than you do at the end. So if I start reading, so if I'm transferring money from A to B, and I read A, and I've backed up A, and then someone transfers that money to B, and then I read B, I've lost some of that transactional consistency in my backup. And so it takes some thought to avoid that kind of problem. The other thing I should have mentioned is I'm going to be using the App Engine data store again as a case study here, because we evaluated all of these techniques for multi-homing the data store and multi-homing App Engine in general. We did this with the data store. When we first dog-fooded App Engine, we do a lot of what we call dog-fooding at Google. We iterate and make people use our stuff internally, often when it's not so good. And so people get sick of this at Google. You're using a ton of stuff that's very early, and sometimes it works, sometimes it doesn't. But the benefit is you get to iterate, and you have users constantly using your stuff, and you can iterate 20, 30, 50 times on something before you're ready to launch it. And there's huge value. Again, it's early, and so when we first started dog-fooding App Engine internally at Google, backups were good enough. We were okay with that. But clearly, it's not good enough for a production system, so we need to keep looking. But as we evaluate, we see there's a lot of red there. There's some green, too. Backups are totally offline. They don't affect how your storage system works. So your latency and your throughput don't change. Assuming you have good latency and good throughput, it stays that way. The rest of it is not so good. You're going to lose all your data if something happens since the last backup. Moving to another data center, you got to back up and restore. While you do that move, you're down. As we talked about, usually consistency and transaction support is weak. Let's see if we can do better. Master-slave replication. This is basically the same as what we talked about with primary and hot failover data centers for multi-homing. Again, like we talked about, MySQL is very commonly used, but most relational databases support something like this. The replication is asynchronous. It's in the background, so it doesn't affect your online writes, which means like backups, you generally keep the throughput and the latency that you had before you turned this on, generally. Similar to backups, the consistency and transaction support that you get from this, if you work hard, you can get decent support, but often you're just kind of sending data as it comes in. You're just kind of blindly moving everything over. And so if you get cut off halfway through a transaction or something like that, the state of the data that is in your replica is uncertain. And so, like backups, you can design it to do better, but it's non-trivial. You got to think about that ahead of time. So this is actually what we currently do with the data store. The consistency and transaction stuff, we put the time in. We figured that out. The catch here is that with end-user applications, you can do a lot better. You can do that whole two-phase commit thing, or even better, and hide it behind AJAX or whatever, so that latency hit that you're paying for, your users don't see. We're offering a much lower level abstraction. Honestly, our competition is as much relational databases living in the same data center, like one machine over right next to you, your app servers, as it is Amazon SimpleDB or Azure Tables or anything like that. Updates or inserts into a relational database, low milliseconds. Our average write on App Engine is already much higher. You're talking 30, 40 milliseconds. It's a different model. Reads in Exchange are often much faster, and we like that trade-off because on the web, reads outnumber writes vastly. But the problem is truly multi-homing the data store, as we're going to see later down the line, would add latency. You would see that latency doubled, if not more, because you'd have to be paying for that round trip between data centers. So most startups, most LAMP stacks, anything that's singly homed, is not even quite that good. So we already feel like there's a win here from multi-homing, and so the trade-off, we said, okay, we're going to try to pick the sweet spot where we give you almost all the benefits of multi-homing and still avoid some of the most egregious costs. There's a better conclusion that I'll get to in a bit, but this is one of the takeaways. This is how we multi-home the data store across multiple data centers. So like we said, depending on how you, this is actually not quite fair. I've given backups a bad rap compared to master-slave on consistency in transactions, but generally it's harder to do those with backups, so I guess that's fair. So if something happens, you have an almost real-time copy of data in your other data center. So you're not going to lose nearly as much data, but you'll lose a little, that small window. And failover, often you can go read-only and serve reads from one of your slave or your replica data centers. But you're not going to serve writes until you have moved your master and you know that, okay, it's in a new data center. I know writes are only going here. Now I can turn them on. Multi-master replication is fascinating. This has been one of the most interesting areas of computer science for a while now. It's a lot of fun. The idea here is that you support writes in multiple places, and you find some way to merge them at some point later. So this is similar. It's asynchronous replication, but you're serving writes in multiple locations, and you've got to figure out what to do with them when there is a collision. The best you can do here is eventual consistency, because writes don't immediately go everywhere. There's a paradigm shift here. We've assumed up until this point that if you have a strongly consistent system, master-slave and backup, we're not affecting how that system runs. We're just doing stuff in the background to help multi-home. Here, we're literally changing the way the system runs because we've got kind of multiple installations, and they're each serving data, and in the background, they have to reconcile. The way you do this in the background, or the way you do the merging is you find a way to serialize. You find a way to impose an ordering across all of your writes. One of the tenets in distributed systems is there is no global clock, or at least there is no global clock you can use. Things happen in parallel, and you can't really ever know what happened when, or at least with regard to each other. So here we make it up. You can have something that hands out what we call monotonically increasing timestamps, timestamps that are guaranteed not to revert. You can use local timestamps with skew detection and other things. You can use local versions. So for a given entity, I don't need to know a global clock. All I need to know is for this entity, what's its version number. You can use a distributed consensus protocol, which we'll get to in a bit. It's kind of putting the cart before a horse, but this is the magic in multi-master and merging writes and reconciling, and there are a number of ways to do it. Like I said, since you're serving writes kind of independently, there's no way to do a global transaction. There's no easy way. You can't offer a read and a write in one data center and guarantee that nothing has happened to it in other data centers that would affect you. For that, you need something stronger that we'll get to in a bit. But you have to kind of accept that this is kind of like multi-threading, where you don't even have locks. Your locks are all in the background after the fact. You do what you're going to do. Someone else does what they're going to do. You figure it out afterward. The result of that is one of the things we care strongly about in the App Engine data store is strong consistency. We feel like this is a key differentiating factor from systems like SimpleDB, which there are a lot of nice properties when you go eventually consistent, but using it to build an application, using it as infrastructure, it's just a lot harder. That mental model of I do something, and I don't know when it's reflected, when it's visible. That's a lot harder to use. So we didn't really consider this much for the App Engine data store because it would have been harder to provide strong consistency. We started with that. The last thing we want to do is take it away from you, So what do the trade-offs look like for a multi-master replication? We lost some transaction support. But in exchange, we don't have to go read-only for failover. Every data center is doing writes on its own, serving both reads and writes. And so if you have to move one or take one down, the others can still handle the writes. So it's a trade-off. Two-phase commit, this is what I started to talk about with NASDAQ, and many of you might be familiar with this if you have database backgrounds. So this is a protocol for doing transactions across separate systems, or at least separate shards of a database, that kind of thing, where there's no single master that everything goes through. I call this semi-distributed because there is always a master or a coordinator for a given two-phase commit transaction. You have to pick one of them. Usually you impose a total ordering at the beginning of all of your nodes, and so that you know for any set of nodes who's the master. Oh, it's the one with the lowest ID, or or you just ask someone. They say, oh, this is the master out of this set. That works when you have very broadly sharded data or highly sharded data. So in App Engine, we have this concept of entity groups, where every entity is in an entity group, and we say each entity group should be roughly the size of a user's data, more or less. One of our large applications, BuddyPoke, has 40 million users, or last they reported it had 40 million users. And so that's 40 million different shards and different possible nodes to participate in two-phase commit. If you did that, or in that setting, saying, okay, there's one master per two-phase commit transaction is not such a big deal, because you got 40 million to choose from, and any transaction is only going to use a few of them. With data centers, you don't have 40 million data centers. You usually have like 3, maybe 5, maybe 10 if you're really big, but it's, what? Do some math, 10, 12 orders of magnitude difference. What you're going to find is that if you use two-phase commit, often one or a small subset of your data centers tends to be the master, depending on how many participate in each transaction. So it's only semi-distributed in that sense. You're often going through the same masters. So what else do I want to say about two-phase commit? Because of that, it's so the next interesting thing about two-phase commit is it's synchronous. For a given master, all two-phase commit transactions are serialized through that master, which kind of kills your throughput. Also hurts your latency. There's a variant called three-phase commit, which lets you do async, but it doesn't get rid of that per transaction master. So we care about data write throughput in the data store, and so like multi-master, we never seriously considered this. We want, scaling is important to us, and any single or semi-single point of failure or serialization point, it's just not going to fly with us. But on the plus side, it works. This is the first kind of true multi-homing technique that we have seen, where you can transactionally, atomically, write something to either 2 data centers or none, and that's really powerful. NASDAQ clearly thought so. So again, this is the biggest paradigm shift we're going to see. Up until here, we have seen kind of offline, background, asynchronous replication and reconciling. This is the first technique we've seen that does synchronous, like online. You report back to the user on a put or insert or update. Yes, it hit both data centers, or no, it hit neither of them. And as you can see that in the colors, it's the opposite, right? Out of the box, you get strong consistency, you get full transaction support. If any one data center falls in the ocean, doesn't matter. You know everything that mattered, everything that you reported success on is in the other one. Same with failover. Generally, you need what we call at least n+1. So if you're serving out of n data centers, you need at least one more, so that whenever you need to take one down temporarily to do maintenance or to move things, you still got that n for the duration. You pay for it with latency and throughput, as I mentioned. The last thing we're going to look at is what's called Paxos. And I'm sure people in the audience can correct me. I believe it was it Leslie Lamport or Bruce? I think it was Leslie Lamport. If anyone knows different, yell out. But he wrote this great paper about, I believe it was philosophers on a Greek island, the island of Paxos, and it was totally esoteric and obscure, and you read the paper, and it was a fun story, and at the end you had no idea what he was proposing, but you knew he was onto something big. I've read the paper. I don't pretend to understand it. I learned Paxos from other people at Google who are much smarter than me, and even then it's non-trivial, but it works. So like two-phase commit, Paxos is what we call a consensus protocol. You have a group of independent nodes, and you want to reach consensus among at least a majority of them, if not all of them, on something. Unlike two-phase commit, Paxos is fully distributed. There is no single master for any given transaction. And again, as I put the slide up, everyone reads first and then turns back and listens. And so you've already read the joke. But the joke here is that a really smart guy at Google named Mike Burrows says every consensus protocol out there, or every fully distributed consensus protocol, is either Paxos or Paxos with cruft or broken. And I don't think he's been proven wrong yet. And so, I'm not going to be the one to bet against him. Like I said, the actual protocol, the Paxos protocol, is similar to two-phase commit, which I didn't even really talk through. There's a propose step, and then basically an agree step or a notify step. Similar to two-phase commits, with the difference that you only need a majority. You don't need the master running things. So as long as a majority of your nodes that are participating in Paxos, or a majority of your data centers, come back and say, yes, I agree, we are here now. We're at this position in the log, or yes, I agree, this has been persisted, then you're good. Like I said, underneath, similar to two-phase commit, the nice thing is there's less serialization. It's distributed, but it can also, you can run multiple Paxos rounds, multiple Paxos transactions in parallel. It's not serialized on whatever, per data center. You're not going to have this serial pipe that every two-phase transaction is going to go through one at a time, which gives you better throughput. The problem here, and then I didn't quite get into enough with two-phase commit, so if we saw this huge drop in latency in two-phase commit. The reason there is, again, you're doing everything online. You're waiting for those round trips. It's actually 2 round trips between data centers before you can go back to the user and say, yes, your write went in. This is where you see writes, 100, 150, depending on how far your data centers are away and how many are participating, 200, 250 milliseconds, which is a long time. And so you see that with Paxos too. Still high latency. You can't avoid that. If you want true multi-homing, you're going to pay for it. We really wanted to do this for the App Engine data store. It's just the right thing for so many reasons, and we use it in so many other parts of Google. We really wanted to. We couldn't quite get it to work with the latency guarantees that we needed to pass on, or not guarantees, but we couldn't, in all honesty, tell you all, writes right now are 30, 40, 50 milliseconds. They're going to be 150. Just trust us that it's better. Just trust us. It wouldn't quite fly. And we can describe exactly why for reasons like this. But fighting against 5 millisecond updates and inserts in databases, that's a tough battle to win. We tried some variations. We tried physically close together, just like NASDAQ with those 27 miles. It helped a little, but you can't avoid the fact that you're doing 2 round trips across lots of routers and queues in between, or routing and queuing delays in between. We even tried putting 2 nodes in the same data center, which would give you a weaker set of guarantees, but at least those round trips are within a data center. And even then, it's not great. You still have to hit at least some of the other nodes. What we can do is let you opt in to something like Paxos, and I'll talk more about this later. Having said that, we use Paxos a ton in App Engine. It's used in a lock server that Google uses very heavily, and we use that in App Engine, usually via the lock server, but some on our own for coordinating anything that we do across data centers, particularly anything where we move state. If your app is serving in one place and we need to move it to serve in another place, we coordinate that with Paxos. Memcache. Memcache has interesting multi-homing of its own, and coordinating, managing that. We use Paxos. Offline processing is the same thing. You'll hear more about offline processing tomorrow at 10:45, and I encourage you, if there's one App Engine talk you go to, don't make it this one, but too late. The one this morning from Alon Levi, which describes how App Engine works, was great. But the offline processing one tomorrow at 10:45, we're excited about that. We're looking for you all to try it out. So check that out. That uses Paxos under the hood too. So this is the final diagram, the kind of final evaluation. You'll see that the only change, like I talked about between Paxos and two-phase commit, is that you get better throughput. The really sad thing here, the part that makes me cry into my pillow at night, and I'm only half joking, there's no fully green bar. you can't find anything on that diagram that makes you happy, that gets everything that gets everything right. It's disappointing. It makes me sad. And so we picked one that had green and yellow. Life is trade-offs. It's no fun, but it's a fact of life. Conclusion, again, no silver bullet. There is no vertical green slice. You still got to do it, though. That 2-hour outage in SV Colo, that's just unacceptable. Much less if there was something destructive and you actually lost data. That's fundamentally unacceptable. It's just not okay. The other trade-off that I'm looking forward to talking more about eventually is, again, that this is inherently a trade-off. Some apps need one thing, some apps need another. We're a platform, and we're a pretty high-level platform, but honestly, we don't know what's right for you. You know what's right for you. If you're a bank, you want Paxos. You want two-phase commit across maybe 2 or more data centers. If you are if you're a game, you don't really care. You just want fast responses. And so what we'd like to do in the future is offer, give you the option. Say, okay, if you want what we call strong rights, if you want two-phase commit or Paxos across data centers, you can do it. Just tell us on a per-right basis or maybe on a per-entity group basis. On the other hand, if you want fast writes and highly available writes, if you want to read from one of those replica data centers, and you're okay with giving up the guarantee that it's always strongly consistent, maybe 1 in 100 times you'll get stale data because the update that you just did hadn't made it to that data center yet, tell us on a per-write basis, and we can do that, or hopefully in the future. We talk about this a lot internally at Google, where there's no one-size-fits-all. And so we want to embrace that. We do that internally, and App Engine is just infrastructure like anything else. We want to let you all choose. That's it. I've taken much more time than I expected. So feel free to come up to the mics and ask questions, and I'm going to go to moderator and answer a few questions there too. Let's see if there's anything there. Perfect. So I'll trade off. What is Google going to do about providing storage, as discussed a bit in the keynote this morning? Is Google going to attempt to compete with S3, et cetera? Good question. So we do plan to offer more options for storing blob data in App Engine, particularly blob data larger than 1 megabyte, because that's the limit in the data store right now. I don't have any particular announcements, but we are working on that. We're excited about that. I tend to kind of live in the App Engine bubble, and so, I pay attention to the other stuff, but I'm only authoritative on App Engine.
Yeah. Could you talk a little bit about entity groups in Megastore and how that would apply in your cross-data center replication models?
Sure. So entity groups are how we shard or partition data in App Engine. All writes and transactions go through journals or logs at the entity group level. And so within an entity group, all writes and transactions are serialized. That is our unit of consistency. And so under the hood, a lot of the replication and data management we do is via those logs per entity group. So if we were to use multi-master replication, or right now we do master-slave replication, when we replicate, it's at the level of basically a log commit. So whether that was a single entity write, or a batch write that wrote multiple entities to an entity group, or a transaction, that log contains basically the diff, all of the changes. And so what we're going to be replicating is, as a unit, that log for each commit to an entity group. And so that's how we maintain both we maintain consistency across replication, and also how we maintain transactions, so that at any time we can go look at the state of one of those replica data centers, and it will be consistent and consistent with regard to its, consistent with regard to transactions. If I put a lot of data in the data store, what options do I have for backing it up? It's a good question. So if you want to ensure against failures of data centers, catastrophic failures like the ones we're talking about, we would hope that we would do the right thing such that you don't need to. In reality, like I said, much of error is human error, And so sometimes you might upload something that has a bug in your code or anything else. And so you definitely want to back up for that. This is all background. The answer is we have tools for doing high throughput bulk upload and download. And those are shipped with the SDK, and the SDK is open source. So right now I would say bulk upload and download are the way to go.
Hi. So a couple questions. The first one is around use cases. Do you imagine a use case where I'm an enterprise and my data is local to me, and that my application is running on App Engine, and I sync up with you, and you cache the data, and the application can actually run and scale, but my data is still kept locally, or what kind of use cases? And the second question is, how much?
Do you mind if I take them one at a time? So,
sure.
So you're saying you would write an App Engine app that accesses your on-premises data, or you're saying you would synchronize your on-premises data?
So I'm worried about having my data at Google completely, right? Having the data in my enterprise, but running my app on yours. But
right.
Are you thinking of other use cases? Because you didn't start with that, and I'm sort of thinking multi-homing. Since you're shielding a lot with the platform, I don't have control over where the data goes.
Absolutely. So there are a couple of questions here. One is...
That was my second question. But
okay, sure, got it. One is if you have data right now and you want to use App Engine, but you don't want to give up all your control over that data, you want to keep it on premises, or at least keep a copy of it on premise, you can use these bulk upload and download tools to basically synchronize your data. And there are actually people who have written better tools to let you basically upload and download diffs. So just the delta of what happened since you last synchronized. You could even write something that synchronizes online using HTTP APIs that you access via URL fetch, something like that. I wouldn't recommend it. I've worked on a number of systems where you try to synchronize data in multiple places, and it's just inevitably difficult and error-prone, and it bites you in the ass every time, and no fun. You can do it. Honestly, I would recommend against it. The second question is more interesting. Can you choose physically where your app serves or where your data lives? Which is a great question. This came up actually this morning at Alon Levi's talk. So there are regulations like the EU's safe harbor data regulations, which require that data is stored inside the EU, which is honestly I believe one of the main reasons that Amazon started offering a choice. You can have your S3 data live in the US or live in the EU. We want to do that too. I don't have any specific announcements or timeline, but we hear you. We totally understand this is just a fundamental requirement, and we need to do it.
Wouldn't that imply that now I have fine-grained control over where my data goes? So in other words, it breaks your shielding from the platform and scaling for me, because now I have to tell you, and I have to make some decisions, right?
That would give you some control, but the techniques we're talking about here don't care about physically where your data is, and so all of the things that the invariants we want to maintain to make sure your data is safe, like number of replicas, number of physical locations, we would expect to maintain those regardless of physical location. What we'd be giving you is a choice and a way to ensure some guarantees such that make sure all copies of my data are in the EU, for example. We want to do that. I don't have details on how it would work. Honestly, we don't entirely know yet, but we want to.
Okay, thanks.
Yeah. Let me take one more, and then I'll close it down. Can you explain what an entity group is with respect to how data store transactions work? I think I did that before, so I'm actually going to call that. Which technique is the Google Data Store using? We are using master-slave replication across data centers. The main reason is latency. It gives us the best guarantees that we can get without making every data store write take 100, 200 milliseconds. And this is a key takeaway, and I should have been clearer about this. It's definitely one thing I'm telling you right now. I'm going to let you all go. If there are no more questions, I can answer the rest of these offline. But thank you for coming. I appreciate it. Have a good conference.